All right, we've learned how to store numbers in binary and therefore into computer understood terms. So we've covered numbers, so you could call that section how computers store numbers. So that's great to store numbers, but we also need to store things like your name and street addresses and names of states and words and letters of the alphabet. So how do we store letters of the alphabet with binary? Because remember, in the end, everything that's digital, any computer device that's digital, must be stored using only ones and zeros. And we're going to use a system, get my pen here, called Ascii, A-S-C-I-I. It is an acronym. You do not need to know what it stands for. I'll show it to you just in case you're curious here. It is the American Standard Code for Information Interchange. And an ASCII table basically translates letters to numbers. So actually, you're still just storing numbers. We just have a little chart that tells us what each letter of the alphabet represents. So let me show you, and what you do is you can just Google ASCII, and I'll show you a very typical ASCII chart here. Let's see, which one did I pull up earlier? I think it was this one here. So let's look at this chart here. Now, don't worry about all the numbers on here. I'll explain it. Let me see if I can zoom in a little bit. Doesn't want to zoom in. Oh, well. Okay, hope that's a little bit better. Okay, what you're going to see here is, in this column, you have characters. And so, for example, G, you have uppercase G, you have lowercase g, M, N, O, P, Q. You have every letter of the alphabet. You also have symbols like quotation marks and dollar signs and parentheses and commas. You have everything you could ever type is on this list. You have bin, that's binary. We will not use octagonal numbers, that's base 8. You've already seen hexadecimal. You won't need it for this part of this project. And decimal, okay? And that's what you will be using, decimal. So, for example, let's say I asked you to store the word hi, H-I, in computer read binary terms. So step one is pull up this ASCII chart. You can go onto Google and find dozens of ASCII charts. They'll all be the same. And you'll find the first letter, H. And you can, well, actually, in this case, you can just use the binary. I said you wouldn't be using the binary, but you can just write that down. In previous classes, I've had them actually start with 72 and then convert 72 to binary. But that takes a little bit, takes an extra few steps, but you already know how to do that. So let's write this down. It's 1001000. So 1 with 2 zeros followed by 1 with 3 zeros. So let's kind of summarize what we're doing here. In fact, let me just start a whole new page here, kind of make this a little neater here. So if I want to store the word hi, and for some reason I'm using my mouse to do that when I have a tablet here. If I want to store the word hi in English, the English word hi, the letters, the H is equal to 1001000. Let me make sure I wrote that down right. I think that's what I read. 1001000. The I, now I wrote lowercase. Let's make sure we're accurate to what I wrote down. Lowercase I is 1101. Sorry, let me get back to my program here. The I is equal to 1101001. Was that what it was? I can never remember these numbers. 1101001. In decimal, that's number 105. And in binary, it's 1101001. So what the computer would do, now we have a small problem here, okay? And here's what the problem is. Some letters are very large, some letters are very small in their values. Some, which means some would only take, let's just do an example here. If I wanted an exclamation mark, no, let's do an exclamation mark. That's a number 33. Actually, that's not a great example. The problem is some, and in fact, some letters are even larger than this. The problem with that is is how many digits is this? 1, 2, 3, 4, 5, 6, 7. That's 7 digits. And this one happens to be 7 too, but some symbols you'll use will only be 6, some will be 8. So if you in the computer, there is no, that's the end of the letter, here's another. That's the end of a letter, here's another. They just, in the computer, you would see this, 1, 0, 0, 1, 0, 0, 0, 1, 1, 1, sorry, 0, 1, 0, 0, 1. In other words, these two numbers are just crammed together and stored side by side. So how does a computer know where one letter starts and the next stops? It can't always be 7 because some are 7, some are 6, some are 9, or some are 8. So all ASCII values are always 8 characters, 8 digits. Always, always, always. Well, you may ask yourself, wait a minute, you just said this one was 7. That's because you always need to add a 0 to the front of it. Add a 0 to the front of it. They did not do that on that chart. So if you just use that chart, you'd be wrong. So this is actually not correct. The word high inside your computer, deep inside your computer, is 0, 1, 0, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1. Okay, does that kind of make sense? Again, the number 1, 2, 3, 4, 5, 6, 7. So this is where that's the dividing line between one or the other. But the computer does not store any kind of divider. It just reads 8 and 8 and 8 and 8 and just spits out whatever those 8 form. Now, so that would be one type of problem. I give you a short 2, 3, or 4 letter word, and you tell me what does it mean in binary. Or we may reverse it. And I don't have one ready to go, so we'll just use the word high, and let's work backwards. So I may give you, let's pretend you never saw this. You never saw this. And I just give you this. What does that mean? It's like a code. What does that mean? Well, you will divide it in 8, and then you'll convert this to a decimal number. I guess technically if you found a chart that has binary, you could just find the binary equivalent, but let me do it the long way in case you use a chart that only has decimal numbers. This is 1, 2, 4, 8, 16, 32, 64. So that's 64 and 32. That's 96 plus 8 is 106 plus 1 is 107. So remember that's 107. This one is 1, 2, 4, 8, 16, 32, 64. 64 and 8 is 72, and 1 is 73. So we have a 73 and a 107. Let's see if we did that correct. That's by base 10 and base 10. Let's look up our chart again. 73 is, was I off by 1? So I've got a capital I. And 107 was, okay, we made a couple mistakes here because that should have been 105. So again, this is why we check your work. Let's see, whoops, wrong program. Okay, maybe just a math mistake. 64 and 32 is 6, that's 96, and we have an 8. Made a mental mistake here. That should have been 14, carry the 1, 104. And then we have our 1 right here. I didn't add on there yet, so that's 105. So 105, that was a lowercase I, as you can verify. Lowercase I is 105, which was 1101001. And what was the mental mistake we made, or the math mistake we made on this one? It should have been off by 1. Let me make sure. 72. Oh, I think I wrote the number down wrong to begin with because it is, whoops. That should not be a, that should not have been a 1. That was a 0 all along, which subtracts 1, giving us 72. So probably not the best example because I wrote that number wrong at the very beginning. That should have been 0, 1, 0, 0, 1, 0, 0, 0, and then the next number starts. Okay, does that make sense? I think we need to do another one. So let's do the word, what's a very short word like, let's do GCS. Okay, so let's take GCS. So GCS is going to be a 1 and 100111. So let's write that down. Let's start a new page here. So I already forgot the number. So it's a 100. So 1000111. Is that what it was? My mind is, oh, nope, 3 ones. One. All right, so there is our first letter, a C. Let's go ahead and do this right the first time. Let's write down, let's add a 0 in front of that. Let's just get in the habit of always, now let me say that, don't get in the habit of always adding a 0. Count first. Do I need a 0? 1, 2, 3, 4, 5, 6, 7, 8. Yes, okay. So now let's get our C, which is, and to be honest with you, I'm more used to writing down 67 and then converting it myself. So we have 1 and 1, 2, 3, 4 zeros. So we have 1 and 4 zeros. And then we have 2 ones at the end. 1, 2, 3, 4, 5, 6, 7 needs a 0. And then the S is very bottom of the screen, 101, 0011, 101, 101, 0011, 101, 0011, 1, 2, 3, 4, 5, 6, 7, 8. So there is your answer if I asked you to convert GCS to binary. But let's check our work. Let's pretend I just gave you that, and you need to figure out what that is. I just prefer remembering these because I don't like all the ones and zeros. You can see how I'm forgetting ones and zeros, so let's just convert this to make it easy on us. Actually, let's do it a different way. Let's convert this to hexadecimal. That is a 3. That is a 5. That is a 3. Remember, in hexadecimal, we're dividing in groups of 4. So those 4 is a 3. 1, 2, that's a 6. 1, 2, 4. I'm sorry, that's a 4. That is a 7. And that is another 4. So this number is 47. This number is 43. That number is 53. Again, hexadecimal. If you don't like doing that, you don't have to. This is hex. You can convert to decimal. If we do that, let's erase all of the, whoops. Well, it won't let me select anything. There we go. Let's erase all of that. Of course, because it's crooked, it's not going to do it all at one time. So if we were to convert all the way back to decimal, which, to be honest with you, I'm most used to doing, it just gives you a little bit bigger numbers. So we have 1, 2, 4, 8, 16, 32, 64. Excuse me. I won't bother with that because it's a 0. So we cross out, cross out, cross out. We're left with 64 and 16, which is 80, 82, 83. So in decimal numbers, that's 83. This is a 1, 2, 4, 8. And then sometimes another trick is I won't even write it down, but I just can't keep track of what column you're on. So 1, 2, 4, 8, 16, 32, 64. And you may like that better. 64, 62, sorry, 64 plus 2 is 66, 67, base 10. And then we have a 1, 2, 4, 8, 16, 32, 64. So 64 and 4 is 68, 70, 71. Now I hope you're seeing the difference. This was in hexadecimal. These are in decimal numbers. So let's see if I can, in fact, let me see if I can look at both these at the same time. That will make it much easier if we can see all of our numbers at the same time. I'm not sure if I can get it that small too. Okay, so we have, let's do the G first. The G in hex, so just in See this hex column? See how it says 27, 2F3, so you're looking for 47. Ignore the 0x for now. Just forget that that 0x is there. Yeah, I'm going to have to zoom out here. So 47 is right here, and that is equal to, let me zoom out some more, 47 is a G, so that's correct. So you would say, ah, that's a G. So I'm going to write G down here. Then you come back to 43. 43 in that column is a C, or a 67. Were we correct on the 67? Let's check that. Yeah, 67 or 40. Just notice which column. You're using the decimal column here, you're using the hex column here, but they should give you the same answer. So you would say, oh, that was a C. And you come to a 53 hex. 53 hex down here is the same as 83. Let's get rid of that. And that's an S. And what's the 83? Let me make sure my 83 was right. 83, yes. 83 was the same as 53. And that's an S. And so you'd say, oh, that's an S. Whoops. Let me write that with my tablet. S. So you would say this string of numbers is equal to G, C, S. And that's how a computer actually stores that. When we type GCS in Microsoft Word, the computer does not store GCS. It stores these. And how does it store it? It stores it in transistors, just like we've learned in past videos. Only ones and zeros. If this was a punch card, let me kind of come full circle back to that old punch card. If you recall that punch card, and remember, I have some in my classroom. If you want, this would be a good time to look at them and see exactly how that works. Now, they may have allowed for more than 8, but a lot of them had at least 8. 1, 2, 3, 4, 5, 6, 7, 8 holes. Okay? This one was punched, and the last 3 were punched. And that would have told the computer, store that value, which if we wanted to print it out, would have been a G. On the next row, it would have been, let's see, and the last 2 were punched. I know this does not show up. The last 2 were punched, and the second one was punched. And that says 0, 1, 0, 0, 0, 0, 1, 1, and that would have converted to a C. So using binary numbers, that's how, even way back in the 1800s, Herman Hollerith was storing people's names and what city they lived in and what their occupation was, all on these cards that the computer, well, his tabulating device, and of course into the 1970s and 80s, the punch cards on newer computers would have quickly read that and said, oh, that's GCS. Just that fast. So that is binary numbers converting to hexadecimal. And in this video, we use Ascii. Let me remember, this whole table is called Ascii. It was developed way back in the 1960s. Herman Hollerith must have had a different system, but the Ascii system, those particular numbers were developed back in the 60s. And so Ascii is a way of converting letters to numbers and numbers to letters. And remember, they're in groups of 8, always groups of 8. So if your number happens to be 7, you have to pad the number with a 0, which doesn't change the value if you add it to that end. Don't add a 0 to this end. That changes everything. So bad, bad, bad. Add it to the front, and you won't change the number. It's like saying 03. That's a 2-digit number, but it's still 3. So that's Ascii. Know how to convert both to words and from words to binary numbers, and that will finish up Ascii values.